A very good evening to everyone. Myself, Dr. Bavita Strangu Kola, and I teach botany in the Department of Botany, Zakir Hussain Delhi College, University of Delhi. It's an honor for me to introduce Dr. Gyan Prakash Singh, Professor of Statistics in the Department of Statistics, Banaras Hindu University, Varanasi. Sir has an experience of over 2 decades in teaching and research. And before joining BHU, he worked in the Department of Community Medicine, Institute of Medical Sciences, BHU, where his key role was to equip the postgraduate students of health statistics in the field of biostatistics. Due to his deep understanding of the subject and dedication, the Department of Biostatistics became the Centre for Biostatistics. He introduced Bayesian data analysis in the course curriculum of M.Sc students. He served in many reputed organizations like Allahabad Degree College, University of Allahabad, and as assistant coordinator of IGNOU Study Center, Allahabad Degree College. He started his career as Statistical Inspector in the Department of Agricultural Statistics and Crop Insurance, Govt of Uttar Pradesh, where he actually learned about the application of statistical theories. He specializes in probability, classical and Bayesian inference, operations research, and multivariate techniques. Sir has given over 300 invited talks all over the country on application of statistics. He has conducted workshops on understanding statistics by MS Excel and SPSS, where he taught the basic concepts of statistics to applied users without using mathematics. He is a member of different academic bodies like Indian Association of Population Studies, Indian Association of Preventive and Social Medicine, ICSSR, and presently he is Secretary of Indian Bayesian Society. He has, to his credit, 65 research publications, and under his guidance, 5 PhD students and 16 MD theses have been awarded. Currently, Sir is involved in the use of Bayesian method in the field of population projections and child mortality. Thank you. Over to you, sir.
आप सभी को नमस्कार. Today I am going to discuss on correlation and the topic given by the organizers. Myself, Gyan Prakash Singh, and I am in teaching profession in Banaras Hindu University, and I am I have started a video channel also on YouTube channel. So if you find the lectures fruitful, then you can go on the site by searching Gyan Prakash Singh Statistics in search of YouTube. So what is correlation? Why we know are eager to know the correlation? I will discuss these things. Before that, I will talk on the data type. So what is the meaning of univariate and bivariate data? To discuss these things, first I have taken an example. Suppose I am having a data set on a variable x which is defined as age of plants in month. So if anyone wants to see this data on graph or graphical representation of this data, then what we will do, we will take a graph paper, we draw a line, and on this line, we locate these points, and the points are called the data points. So in this case, these points are my data points. Now, what we do in analysis of these points or this data, we generally find a number which lies in between these numbers called measure of central tendency. And then we find another number which is supposed as distance of this point, my mean point, from individual points of the data. That is called dispersion or standard deviation in quantitative case. So if for this data, we have mean 46 and SD 20 month, and the mean is 46 month. Apart from this, we can calculate so many other numerical value to know different characteristics of this X and those values are generally mean, median, standard deviation, kurtosis, etc. At the same time, suppose I have collected another data set on another variable number of branches in these trees. But is this time in this at this time I'm not interested in X, I'm interested in only Y. So if it is so, I will have another line of points, and this point also has these type of characteristics, which is univariate characteristics of the data. So at this point of time, I have discussed you two different variables. One is age of plant, another is number of branches, but I'm seeing both the lines or both the data independently. So if you are doing your analysis like this, it is called univariate analysis of variable X, variable Y. Now suppose that in place of seeing the data in that way, we are interested in seeing this data point. X is age of plants, Y is number of branches, but we are not interested, we are not seeing it differently or independently. Now we are seeing in simultaneously, both the points simultaneously. Then how our data will look like in the graph paper? It will be like this. Initially, X was here, Y was here, and we were seeing them not just simultaneously, or we are seeing individually. Now, if we are interested in seeing them simultaneously, then these points are my data points. Now, how we analyze these points? So again, the main idea of analysis is similar to the univariate. Again, we search a point in between these points, which is supposed to represent these points, that is central value, and then we search another point, which is called dispersion or distance, which shows the distance of these points from center points. And that is, the distance is also called variability of the data. So we may be interested in center point, central value, and variability. Now the variability is termed as, in bivariate case, it is termed as covariation. So we are interested in bivariate analysis. Our interest lies in covariances, how the values are varying, covarying. So when we have paired data or bivariate data for two variables, then statistical methods to measure their variation is termed as covariation and defined as covariation of xy paired variables is equals to arithmetic mean, sum divided by n. So arithmetic mean of product of deviations of x and y. Deviations of x means x minus x bar, distance of center of x from individual x values, distance of center of y from individual y values. So if it is a scatter diagram, and this is my central value x bar, y bar, 46, 36, then we will see what is the distance of this point from these individual points, and then we product those distances to calculate covariation like this. This we calculated x mean of this x, mean of y, then we subtracted x minus mean, y minus mean, and then we take the product of these differences and then arithmetic mean to get the covariance. So the covariance of this data set, covariability of this data set is 229.6. Now here a question arises whether this 229.6 is unit free or it has unit. So it will have unit because x was in month. So x bar will be in month, x minus x bar will be in month. Similarly, y was counting number of branches. So it will have a unit. So 14 unit, 20 unit, 22 unit, 25 unit, like that. So y minus y bar also have units. So product will have two units, first month and second unit. Hence, this covariation is not free from the unit. It will have unit as month cross unit. Now the question arises, what the covariance measures? No doubt it measures covariability. So we know that the variance, we get a single value whose square root shows the average distance of univariate observations from their mean point. In bivariate case, to get a single number which represents the deviation of from both variables from respective mean is covariation. So the covariation is measure of joint variability of two variables. The joint variability may be linear or may not be linear. So what is the meaning of linear? If you are having a scatter diagram and the points of your scatter diagram are on a straight line, then we say that the variability of points is linear. For example, if I have any data set and the scatter diagram of points of bivariate data looks like this, and all these points are on a straight line. So we say that this is a linear relationship. The variability is linear. And in this case, there is variability among the points or data points or paired observations, but the it is corresponding to a curve. So it is called, it is not a straight line type data. So we say that it is non-linear and this scatter diagram is linear. So the covariation or covariance tells about the linear situation in terms of direction. What is the meaning of direction? That whether by increase in the value of x variable, there is increase in the value of y variable. In this case, we are getting this. So here it says it is a positive direction. So if covariance value is positive, then the values will move in positive direction. If the covariance is negative value, the calculation of covariance comes to be negative, it means that my one variable is moving in one direction, then the corresponding other corresponding value of other variable is moving in negative direction or inverse direction. And in that case, we say the correlation is negative. So the value of correlation coefficient informs us direction. Now the question arises whether it also measures the strength. So what is meaning of strength? Strength, by the meaning in the bivariate analysis, by the meaning of by the word strength, we mean that whether the covariation of our data point is towards a particular straight line, whether my data points are on a straight line. So by seeing the value of covariance, we can't say whether if we make a scatter diagram, then my points of a scatter diagram will come on a straight line or they will deviate from the straight line. So the strength is not judged by covariance because of certain reasons. I will discuss why it only provides idea of direction, not the strength of the relationship. So covariance tells only about direction of relationship. Why I'm saying like that? Suppose I'm having this paired observation, which we are discussing earlier, and our scatter diagram is this. And if we calculate covariance, we have seen that its value was 0.229.58 month into unit. Now, suppose we are having another data set of similar type of variation. another data set of similar type of variation like this. Now my variable is W and U. How I get this data? In my original data, I multiplied by 10. The value of X multiplied by 10, value of Y multiplied by 10. It is just for example. You can multiply by any value, you can divide by any value. So whatever you, if you are choosing divide by 10, again yours, the nature of this data will not change. So if I transform my data and if I want to see whether what is the scatter diagram is of this data, so you can see that the scatter diagram of this data is similar to the original data. This is transformed data, transformed paired observation, and this was original. Both are having similar variation. But if I calculate covariance of this data, it will not come to this one. If I calculate W minus W bar, calculated mean, then W minus W bar, U minus U bar, then product, and then mean. So this is covariance. This is covariance. Now you can see that both are having different value of covariance, though they are having same sign. Means they are saying that the movement is in positive direction, X is increasing, Y is increasing. So movement is positive direction, both are saying, but the amount of covariation is different for these two. Hence, the strength of relationship can't be measured by covariation because we are having the unit of measurement in covariation. Hence, we saw that both data, bivariate data were having similar scatter diagram, but covariance of observed bivariate data and transformed bivariate data are not same. Hence, due to measurement unit of variable, we cannot use covariance to know the strength of linear relationship of bivariate data. So, if we are our interest lies to know the relationship strength so that we can model our data. Hence, if you are interested in knowing the strength, then what to do? Now, if you are interested in seeing the strength of relationship, the standardized covariance should be considered. And it was advocated by Carl Pearson that you calculate standardized covariance, and it was named as coefficient of correlation, or Carl Pearson's coefficient of correlation, as it was originated by Carl Pearson, a mathematician, statistician. Now, what is standardized covariance? Standardized covariance is that you transform your data in standard data. Both variables, you transform your both variables in standard data and then calculate covariance. How we transform? I will show you by the example. So it was advocated by, this formula was advocated by Carl Pearson, and it was called correlation coefficient, and it is nothing but it is again covariance of transformed data, transformed in a similar in some specified manner. So suppose we are having so the Carl Pearson's formula, correlation formula, is used in particular case when your both paired variables are quantitative and they have certain assumptions, they fulfill the certain assumptions, then only we calculate Carl Pearson correlation coefficient. However, in real life, the relation can be seen in different type of paired observation, like type of plant. My variable is X, type of plant, and my data is that 0 if plant is fruit, 0 if plant is fruit plant, and 1 if plant is a non-fruit plant, and a number of branches Y. So my X is qualitative and Y is quantitative. And X is having only two qualities, fruit plant and non-fruit plant. Now, if you want to see the covariation of the paired observation 114, 0, 20 like that, you can use Karl Pearson coefficient formula or you can use t-test. The situation may be like this. Both of the variables of your bivariate data are qualitative, like type of plant, fruit, non-fruit, and return from the plant means if it is fruit, then high return means 1 and low return means 0. Oh, sorry, 0 means high return, 1 means low return. And in this way, your bivariate data is both bivariates observations are qualitative. So if you are interested in this situation, knowing the relationship, then you have to go for some other techniques that is called correlation or association of attributes. Okay, but I am restricting myself on quantitative analysis. Or quantitative bivariate data means the Pearson's correlation coefficient. So let us consider standardized covariance, which was educated by Karl Pearson. So this is my data set. Now what I will do, I will standardize these X and Y by defined manner. What is the defined manner? We take the mean of X, that is 46, standard deviation of X data, that is 19.82, and then we subtract from each value the mean value 46. And then we divide each subtraction X minus X bar by ST. We will get the data like this. Similarly, for Y, we get the data like this. So this is standard X data, and this is standard Y data. The beauty of this standardization is that whatever the value is in your, for your original data set, if you standardize and then calculate mean of this data set, you will get always 0 as mean and 1 as its variance. So this data also has mean 0, variance 1. This transformed data also has mean 0 and variance 1. Now, if we calculate covariance of these paired observations, so mean is 0 for everyone. So X minus X bar means the same value, Y minus Y bar means the same value, and hence the product is this. And if you take mean of this, then it is covariance. And nothing, it is correlation coefficient of Karl Pearson. So we calculated this product and then we added from here to here, and addition was the value sum was 9.951, and I divided by 12 because there were 12 pairs. Hence the value is 0.83 in my original data set, and it is called Karl Pearson correlation coefficient formula. Okay, now when we calculate Karl Pearson coefficient formula, and then if you are having a standardized data set and you are calculating Karl Pearson's, if your formula is, if your correlation coefficient is coming positive, your scatter diagram will lie, the points of your scatter diagram will lie on first and third quadrant. If correlation coefficient is negative, then the point of scatter diagram of standardized data set, paired data, will lie in second and fourth. You can remember that the original data set was having scattered point in first quadrant. All were having in first quadrant. But this standardized data set is having points in first and third data set quadrant. Hence, it is clear that the positive, there will be positive sign. Now, let us consider the transformed data set, which was having different covariance in a previous discussion. Again, we calculated mean and standard deviation of this transformed X, transformed Y, that was multiplied by 10. I am naming it W and U. Now we transformed this as a standard data set, and then we calculated correlation coefficient, means the mean of this product standardized value, and it will be 8 to 9. So we are seeing that this standardized data set in both cases providing same covariance, it means same correlation. So there is no effect of transforming the data set on correlation coefficient. How it was being affected by in case of covariance. So what is difference between covariance and correlation? It both are mathematical concept, both measure dependency, both tells about dependency. One tells about the direction and another tells that direction as well as strength. So if you are, now the question is which one should be used? So if you are interested to say something like this, a change in one variable is bringing change in another variable, then we take the help of correlation coefficient. We provide this type of statement by the help of correlation coefficient. On the other hand, if we are interested to say how they are varying, how they are covariating, then we take use of covariance. So a measure used to indicate the extent to which random variables change in tandem is known as covariance. Both measures covariance with different information about linear relation. The value of correlation coefficient takes place between -1 to 1 and covariance between -infinity to infinity. Now, if covariance is +1, means my data is both the points are moving in same direction. If x is increasing, y is increasing, y is increasing, x is increasing, x is decreasing, y is decreasing. But if it is minus, then the movement is vice versa, or reciprocal movement is found between the pairs or pair of variables. The coefficient of correlation is unit-free, hence comparable with, while covariance is not unit-free. Hence, now the question is, which one is the better choice for bivariate dependency measure? No doubt, correlation coefficient is better choice. It is preferred over covariance, though technically, if we see, both are same thing, covariance and correlation. The only difference is that correlation is standardized covariance. But this standardized provides us extra information about strength of the relationship. So if we are having data set and all our points lies on a straight line, in that case, we say they are perfectly related and it is perfect linear relation. So strength of relationship is said perfect. In this type of scatter diagram, we say that since the points are not, all points are not on a straight line, hence the relationship is not perfect, but there is a strong linear relationship. And in this case, third case, the relationship is again linear type, but the situation is reverse. One variable is increasing, another is decreasing. And in this case, another situation arises. The variables are moving inversely, but all points are not on a straight line. Then we say that there is weak linearity, means variables are moving inversely. In first case, if you calculate a correlation coefficient for this type of data set, you will get its value +1 always. Here, if you calculate correlation coefficient, you get a value of correlation coefficient between 0 to 1. As close this point will be nearer to this straight line, it will be closer to 1. Here it is case of R is equals to -1. Correlation coefficient, generally correlation coefficient is denoted by R. So it is -1, and here it is -1 to 0. So seeing the correlation, seeing the scatter diagram, you can have idea about the strength of relationship. So if all points are on a straight line, the strength is perfect, or will be either plus or minus like this. And if the points are moving or dispersed just slightly from straight line, then the range of R will vary from 0 to 1 or -1 to 0. In many situations, this movement of a scatter diagram may be like this. It is called curvilinear, and hence it is not a linear type relationship. But if you still want to calculate standardized covariance in this case, again you will get some value, and this value will be -1 to 0, because this is the values are moving inversely to the y. X and Y are moving inversely, not in same direction. And so sometimes if you get this type of situation, it is said that in this type of situation, the correlation, the values are variables are found to be uncorrelated, because here it is not clear that whether X is increasing, then Y is increasing, or X is decreasing, then Y is decreasing, because both type of situation we are seeing here. Hence, in this case, the value of correlation coefficient comes to be 0 or nearer to 0. But when you do correlation coefficient to know the strength, when you calculate correlation coefficient to know the strength of linear relationship, be cautious. You don't use formula directly, because many times you may be in dilemma after seeing the graph. For example, if we are having the data set like paired data like this, X, Y, and if we calculate correlation coefficients, you get a value of correlation coefficient of 0.9. Means this correlation coefficient is saying that my scatter diagram looks like this, more or less. 0.9 correlation coefficient always say a situation like this, the dots may be slightly varying. But if we make the scatter diagram of this data set, this is the situation. This is the situation. Hence, what I'm saying, if you are directly calculating correlation coefficient and saying that the relationship is strong linear by seeing this value, it may be harmful if you are not seeing the scatter diagram. Hence, while calculating the correlation coefficient of Karl Pearson's, it is suggested that you make first scatter diagram and then decide whether or not we calculate correlation coefficient to know the relationship. The interpretation of correlation coefficient is not much difficult. If it is positive, we say that both the variables are moving in same direction, and if its value is closer to 1, we say that the movement is linear. So if X increase, Y increase, if it is positive. So in this case, we say that the age of plant and the number of branches, we say that X and Y are positively correlated, and evidence of a linear relationship is very strong. More is the plant age, more are the branches, or vice versa. You can say that less is the plant age, less the number of branches in plant. When we say relationship, then mathematically one variable. When we say relation in mathematics, then what happened? If we are talking about two variables, then we treat one variable as dependent and another variable as independent. But when we say linear relationship on the basis of R, we are not able to say which one is dependent and which one is independent. So while interpreting this, we avoid any statement like this. Okay? If this increase, X increase, so Y increase. It has another meaning. If Y increase, X increase. Okay, so we can't define on the basis of which one is increasing. Okay, so be cautious about that. And generally, when if you getting a value of R, it do not say that there is no correlation, no linear relation. We only say that there is no linear relation, though there may be strong another type of relation, curvilinear relation. Correlation coefficient shows the strength of linear relationship between xy. Thus, even if there is a strong nonlinear relationship between xy, the value of R may be very high, as we see in the previous scatter diagram, or it may be low. The correlation between two variables indicates that the change in one variable are associated with change in other variable. However, it is not a causal effect. It does not say that due to this variable, there is change in that variable. So if you are uh, giving the statement like that, avoid these type of statements on the basis of correlation coefficient. Generally, what happens when we calculate correlation coefficient, we calculate on the basis of sample data in researches, and the sample is taken from a population, and we want to infer about population. So if we are calculating sample correlation coefficient, my motive will be to infer the correlation of population. So how we do, we take the help of correlation coefficient, hypothesis test in this situation. So we take a null hypothesis that pair of variables in population are uncorrelated, that is population correlation coefficient is 0. Here I think it should not be small r is sample correlation coefficient, it will be capital R or rho. Generally people like rho. So here you treat it as rho, not this small r. It is sample correlation coefficient. So my null hypothesis is that population correlation coefficient is 0. The alternate is that no, that is not 0. Rho is not equal to 0. Now, how we test this hypothesis? We test this hypothesis on certain probability distribution, on the basis of certain probability distribution of certain test formula. So what probability distribution we use in the significance of R? We use T probability distribution in the testing the significance of R, and how this T probability value is calculated, T value is calculated, we use this formula. Sample correlation coefficient, that is R, which I have calculated, minus correlation coefficient value under H naught, that is 0, upon standard error of sample correlation. Since in H naught this value is always 0, so you can reduce this formula like this, and again this is equals to sample correlation coefficient upon standard error of correlation coefficient. Now the standard error of sample correlation coefficient is calculated as or formulated as 1 minus r square upon n minus 2. N is the number of observations in the sample, paired number of pairs. And whatever the value we calculated, it is called calculated value of T. Now, on the basis of this calculated value, this is called test formula. On the basis of calculated value of T, we calculate P value of this calculated value, that is called probability value or P value. And it is calculated as probability of T probability distribution takes any value outside this T calculated. When it is supposed that there is no correlation under H naught. Now, if this P value is less than my level of significance of the hypothesis, then we reject null hypothesis. Okay. Now, let us consider our example. In our example, sample correlation coefficient was 8 to 9. My hypothesis is that there is no correlation in population. I calculated T value as 4.69 by putting the informations in this formula. Now we will be interested in knowing what is P value. So to calculate P value, If you are using Excel, you type in any cell tdist. So if you type tdist, it will ask some questions. Number one, what it will ask? The value of t or x. So type here 4.69. Then comma, degree of freedom. Degree of freedom will be n minus 2, so 10. Then it will ask test hypothesis. So you type here 2 because my alternative is taking both sides are row less than equals to 0, row greater than equals to 0. So it will be 2 hard tell. Now as you enter, you will get a number between 0 to 1, which is p-value. If this p-value is less than your level of significance, generally which is kept as 5%, so you can say that your null hypothesis is rejected. In our case, my p-value is less than 0.05, hence we say that null hypothesis is rejected at 10 degree of freedom and 5% level of significance, means the population correlation coefficient is not 0. The variables, the two variables, age of plant and this number of branches in plants are positively correlated, and they are strongly linearly related, these two variables, as the correlation coefficient is 0.829. Okay, so it is also called my correlation coefficient is significant. This relationship between variable is significant. On the other hand, suppose this p-value comes as 0.09, which is greater than 0.05. In that case, we say that no, there is no relation between age of plant and a number of branches in population. And whatever the relationship we are seeing from sample, it is by chance. Okay. So this is the interpretation of significance of correlation coefficient in inferential statistics and inferential analysis. Now, what type of data we need for correlation coefficient? Certainly, it should be quantitative, continuous type, and bivariate normality should be there. The pairs should be related. Both variables should be meaningful, such that you can observe the simultaneous relationship. Your data must be free from the outliers. So you can check the outlier for the data set. In checking of the outlier, generally people check the outlier individually for variable X, individually for variable Y. But it's better to check the bivariate outlier, means bivariate normal distribution outlier. A linearity must be there, so you have to see your scatter diagram whether your points are moving in a linear direction, means towards a straight line, closer to a straight line, or closer to a curve. So if it looks like closer to a straight line, then only you go for Karl Pearson correlation coefficients formula for calculation of correlation. If you found that your data is not meeting the requirement of calculation of correlation formula, then you can use some other methods for the relationship to know the relationship, and they are many by names, that is rank correlation, phi coefficient, Kramer's V coefficients, odds ratio, etc. Now I'm going to discuss a little bit a different concept, that is multiple and partial correlation. Generally, what happens when we do studies, we do not only rely on two variables. We have so many variables in our study, and we want to analyze our data. And doing so, we do more accuracy with the data analysis. Now, I'm considering an example. Suppose we are having a data set in which there are 4 variables: funding, disease, visits, and city code. This example, which I am going to show you, is taken from the SPSS example file. So I'm mentioning it. What is meaning of funding? The meaning of funding data is that it is the amount of fund, healthcare fund given by government on per 100%. A disease means among per 10,000 person, how many diseases were reported. And visit means per 10,000 person, how many healthcare providers visited in the field. Now, this data has this type of uh, looks in the SPSS data file. So these four are a city code. City code is means in which city these observations were made. Okay, so in SPSS there are 50 cities data of funding, disease, and visits. Now, if you see bivariate data, funding, and disease. So this is amount of fund given by government, and this is disease information, that how many disease were reported in that city against this funding. Generally, if we talk about the relationship, people may say that there will be negative correlation, because if we increase the fund, the disease must decrease. So there will be negative correlation. But if we calculate correlation coefficient, you will get a correlation value of 0.737, means positive correlation. Means disease is increasing, funding is increasing, both are increasing. And this study is significant also because its p-value is 0.00. Now, the question arises, why it is so? The common perception is that if we increase funding, disease must be decreasing. So why it is positive here? So in real life, when we talk about relationship of two variables, those variables may be affected by some other variable which are not taken in study. And the relationship what we are seeing may be due to that variable. For example, here, what is the situation? Due to increase in fund, this variable is increasing. Visit is increasing, means more doctors are recruited, more nurses are recruited, and the people are going in field, and more visits are increasing due to increase in the funding, healthcare funding. And due to increase in visit, the disease reporting is increasing, because before that, when the less funding was there, people do not go in field much number, hence many reports were not, many disease were unreported. So due to increase in funding, disease visit is increasing, and the visit increase, disease counting. Okay, so the funding and disease both are being affected by visit. And hence, since visit is not taken in consideration, hence we are seeing this high positive correlation. So what is the remedy? Remedy is that if we are interested in seeing the relationship between these two, we have to neutralize the effect of visit. And if you are interested to do, it is called partial correlation coefficient. So again, if you are interested, you go in SPSS. If you are using SPSS, you put the both in target variables in variable list and the visit in controlling list, and then calculate, click OK. You will get the relationship correlation coefficient as 0.01. Means there is no relationship between funding and number of disease. They are uncorrelated variables, and initially whatever the high correlation was obtained was only due to a third variable, that is called confounder variable, and due to that we were seeing that much high correlation. As soon as we adjusted the effect of that, we get no correlation, and it is also insignificant correlation because p-value is very high. Means there is no relation between health funding and disease reporting. Okay, so this is the role of partial correlation in correlation analysis. And when you are having more than two variables in your study, you always try to know whether partial correlation, see the partial correlation to see the real picture. Okay. Generally, if you are having three variables, this formula calculates partial correlation, but I'm not going to discuss this formula because softwares are available. You have just to know what the analysis I have to do. So if you are having multiple data set, so and you are seeing calculating for bivariate correlation, you also see bivariate partial correlation by keeping the effect of other variables. Multiple correlation is another way of understanding correlation, and that correlation is discussed in will be discussed in the this my next video of regression analysis, which is in continuation of this one. So for the time being, I thanks to all of you for seeing this video. Thank you very much.